Hi everyone, today I would like to talk about two very important concepts. One is orthogonality principle, which is extremely important concept used in the context of MMSE and also in the estimation context in general. Two, I would like to discuss about MMSE estimation after observing more data or after collecting more data, meaning that in first part of this MMSE estimation series, I discuss what happens when you want to estimate a random variable x given a constant, using a constant. And then I saw another example that how can you estimate a random variable x using a linear combination of two other random variables. You can expand this one to n random variables. Today, I would like to talk about what will happen if you want to estimate random variable x. You want to find the estimator for random variable x, given that you have observed another random variable y, which is very, very important concept. Usually, this is the case in the real world, right? Okay, so let's start. First, I am going to talk about the orthogonality principle. Let's see what is that. Orthogonality principle states that the estimator and the residual are perpendicular to each other. So according to orthogonality principle, if you choose an optimal estimator, then it will be perpendicular to the residual. So according to the optimality, according to the orthogonality principle, the estimator, if it's supposed to be optimal, then it will be orthogonal to the residual. Let's demonstrate this one here. So our true value, this is the true value, what we want to estimate. This is x hat, is the estimator, and the epsilon is x minus x hat. This is the residual. Great. So assume we have this plane here. This is x. Let's say this is the x hat. This is our estimator. This is the estimator that we have. Then this one is the residual, x minus x hat, which is residual. So it says that the residual and the estimator are orthogonal to each other. That's all it says, but it's used a lot in various domains. So for example, in the last example that I solved, the objective that I formulated, or the MSE, mean square error, for the last example, if you haven't watched the last video, I will put a link in the description. Please check out the last video that I solved that example, and also the first part of this MMSE estimation videos that I discuss about how to formulate the problem, what's the intuition behind the MMSE, and what's the goal and objective. So we said that we are trying to estimate x1 using linear combination of x2 and x3. So that was this. That was the objective we were trying to minimize, right? So our true value is x1 here, and the estimator is a2, x2 plus a3, x3. So one thing that you can use here, according to orthogonality principle for this example, orthogonality principle here is that here, first write the epsilon, which is residual, is x1 minus x2, a3, x3. This is the residual. So this one will be orthogonal to the actual estimator. Orthogonality, in terms of the expectation, note A and B are orthogonal if expectation of AB is equal to 0. So here we want the expectation of x1 minus a2 x2 a3 x3 times a2 x2 plus a3 x3 to be 0. So that's what you can write about the orthogonality principle, right? But I would claim that this is not really that useful, or it's not really that convenient. That maybe this is a better way to put this. It's not really that convenient, or it's not really that easy to work with. I will call this one equation 1. Let me just go ahead and call this one equation 1. So I will call equation 1 to be this. X minus x hat are perpendicular to x hat. So I will call this one equation 1 as a orthogonality principle. And then this one I call it equation 2. But let's take a look at this diagram with each other. Let me use another color here. Let me use another color. If you look at this one, and if you go back to your geometry class, you remember that if a vector is orthogonal to a plane, then it will be orthogonal to every single vector in that plane, right? So here, the vector x minus x hat, here, vector x minus x hat is orthogonal, this is, let's call it plane P, to plane P. Therefore, it will be orthogonal to every vector in that plane. So, therefore, it will be orthogonal to every vector in the plane. Now, let's talk about this a little bit. This means that it's orthogonal, of course, according to the orthogonality principle to the estimator, which our estimator is this, which means that it's orthogonal to each of these two elements. It's orthogonal to x2, it's orthogonal to x3, right? So you can write the orthogonality principle in a simpler form. Or, this is part A, or B, you can write it like this. The residual times this is 0, times x2 is 0. And times x3 is 0. So now you can get some sort of interesting expression after you simplify this, right? So times x2 is 0 times x3 is 0. You don't need to enter the a2 and a3 here to actually complicate the expression further. So let's use this one, equation 3. Let's use this one, equation 4. So let's write this one a little bit more. So I would say that from 3, if you simplify that, you get this x1, x2 minus expected value of a2, remember, is deterministic, x2 square minus a3 x2 x3 equal to 0. So that would be actually a valid expression. Now you could actually find the estimator using this, right? This is also one way to solve the MMSE problem. Just use the orthogonality principle. Look at this equation. It's very similar to what we got using in the part 2 of this video series. In the last video, I will put a link in the description. And also, I didn't really score anything. I didn't really calculate any MSE. All I used was a orthogonality principle. So that's the first equation. The second one, I will write from equation 4, I get x1, x3 minus a2, x2, x3 minus a3, x3 square equal to 0. So you could just solve this. Two equation, two unknown, and you get the optimal MMSE, right? You get the optimal MMSE using this, only using the orthogonality principle. That shows the power of the orthogonality principle. So my goal was that in part 2, I show you one way to do this, and part 3, this part, another way to solve startup problems. Now you are capable of formulating your problem, MMSE problem, in 2 different ways. Right? Okay. So let's just expand on this problem a little bit further. We move the term that doesn't have a2 or a3 to the right-hand side, and then we multiply everything by negative sign to make everything positive. So you get a2 expected value of x2 plus a3 expected value of x2, x3 is equal to expected value of x1, x2. Now here you get a2 expected value of x2, x3 plus a3 expected value of x3 square equal to expected value of x1, x3. Okay, so now what we're going to do is just form the system of equation in a matrix form, right? So we're gonna get x2 square and then expected value of x2, x3, and then here we're gonna get x2, x3, and then here expected value of x3 square, and then we get a2, we get a3, and then here we get expected value of x1, x2, and expected value of x1, x2. Okay, so this one, remember, this was a vector A for us, this was Z, and this is Y. You see, you get exactly the same thing if you follow this procedure. So that's the power of orthogonality principle. Very fast, you form the estimator, you subtract the estimator from the true value, this forms the residual for you. You have the residual, you multiply that by each vector in the estimator, like x2 and x3. That doesn't matter how many you have. If you have n of them, you will have system of n equation, n unknown. You can solve it in any method you like. Okay, great. Perfect. Now, let's talk about another important concept. So, in the first part of MMSE estimation video series, I talked about how you can estimate the random variable x using a constant y, right? Okay, that was easy. Then I solved an example how you can estimate a random variable xy using linear combination of two random variables, like what I just solved here above. Okay, that was easy too. But what if I tell you, I want to estimate a random variable x using after I observe random variable y equal to a small another y. Right? Now I have some evidence. I have observed some data. I have observed some observation. I want to make some inference. I want to calculate the probability of now x, expected value of x. Right? I want to estimate x. I want to see what is x actually. So it turns out that the best estimator, the best MMSE estimator for a random variable x, after you observe y equal to y, the best estimator for random variable x after observing y equal to y is expected value of x given y equal to y. Okay, so there is a proof for that. I might create a video on how to prove this is the case. I just don't want to make this video complicated. And I want to focus on the intuition. It's very important to understand this one. This one is a very general equation. It's very general. It can be used for any MMSE problem. It's very, very general. So that's a good thing about this equation. Now, what are the bad or disadvantage of this equation? This equation in general is nonlinear and it's complex to calculate. In a lot of real world problems, this equation is not really easy to calculate and is in general nonlinear. Therefore, in usually MMSE problems, we limit ourselves or restrict ourselves to a class of linear MMSE. Therefore, we usually restrict our model to the linear MMSE. And the Kalman filter, which is a very, maybe the most important example of the MMSE, is an example of linear MMSE, linear mean square, linear mean or mean square error estimation. In the next video, I'm going to tell you all you need to know about the linear MMSE, how to estimate the coefficient of linear MMSE, how you can find a closed form solution for the linear MMSE, and how you get a closed form solution for the MSE, given the estimator is linear. So how you find the optimal mean square error, optimal residual, when the estimator is the linear MMSE. So that's it for this video. If you like this video, please subscribe to the channel, share and like this video with your friend. As I said, I have written a article. During that article, I also talk about all this equation that I'm talking to you about them, and also I have talked about the linear MMSE. I have solved a couple of examples about that. I will put a link to that video in the description. Please go ahead and check that video. And thank you so much for listening. See you all in the next video. Thank you.